Hello everyone. So in this lecture we are going to prove this theorem. Prove that an ideal A generated by A naught is maximal ideal of Euclidean ring R if and only if A naught is a prime element of R. Proving this theorem we need to know these three facts. If M is a maximal ideal of any ring R, then Euclidean ring R, then no ideal exists between M and R. अगर M R का कोई मैक्सिमल आइडियल है तो M और R के बीच में कोई भी आइडियल एग्जिस्ट नहीं करेगा. If T is any ideal of R such that M subset T subset R, then either T will be equals to M or T will be equals to R if M is मैक्सिमल आइडियल. अगर M R का कोई एक मैक्सिमल आइडियल है तो और T इन दोनों के बीच में एक आइडियल दिख रहा है तो T या तो M के बराबर होगा या फिर T R के बराबर होगा. If any element A of Euclidean ring R is invertible, then it is an unit element. So, coming to our topic, an ideal A generated by A naught is a maximal ideal if and only if A naught is prime element of R. Let A naught is prime element of R. We are letting this point, so we have to prove that A is maximal ideal of R. Let T is any ideal of R such that it is between A and R. We have to prove that A is maximal ideal of R. For proving this condition, we have to prove that ideal A is equals to T or T is equals to R. Let implies that A naught belongs to T. Let T be ideal generated by B naught. That means A naught is equals to A naught is belongings to this ideal generated by B naught. It means A naught is equal to any element written like this. Or we can say that B naught is dividing A naught. Obviously, A naught is written in product of B naught X. It means B naught is dividing A naught giving X. Here, B naught is dividing A naught and we let that A naught is a prime element of R. A naught is a prime number. So, either B naught will be 1 or B naught will be A naught. Taking first condition, if B naught is equals to 1. If B naught is equals to 1, that means B naught belongs to an ideal generated by 1. To explain this, we should know an identity, or we can say unit principal ideal of a Euclidean ring R is equals to that ring. This is a important note. Any unit principal ideal of a Euclidean ring R is equals to that Euclidean ring. So if B naught is equals to 1, that means ideal generated by B naught belongs to ideal generated by 1. That means ideal T is equals to ideal R. First condition. Second, if B naught is equals to A naught, that means ideal generated by B naught is equals to ideal generated by A naught. It means T is equals to A. So, either T is equals to R or T is equals to A. This means from here A is maximal ideal of R. We have to prove that A generated by A naught is maximal ideal of Euclidean ring R if and only if A naught is prime element of R. Let A naught is prime element of R, then we have to show that A is maximal ideal of Euclidean ring R. A is maximal ideal, then if let T is any ideal of R such that this condition is applicable, then either A will be equals to T or T will be equals to R. Only then A will be the maximal ideal of R. Taking A is a subset of T such that A naught belongs to T. Let the ideal T is generated by its element B naught. That means A naught belongs to ideal generated by B naught. That means A naught can be written in multiple of B naught. So, or we can say that B naught is dividing A naught. Here A is a prime element. A is a prime element. So, either B naught is equals to 1 or B naught is equals to A naught. Any prime number is divisible by itself or 1 by definition. So this condition is written like this. Here we have to remember the point that every unit principal ideal is that ideal. That means every identity or unit ideal of a Euclidean ring R is that Euclidean ring itself. So if B naught is equals to 1, that means ideal generated by B naught is belonging or equals to ideal generated by 1. That means T is equals to R. Second case, if B naught is equals to A naught, that means ideal generated by B naught is equals to ideal generated by A naught. That means T is equals to A. T is equals to A or T is equals to R. That means A is the maximal ideal of R. The first part of this theorem is proved. A is maximal ideal of R. Now we will prove the second part. Conversely, here we will take one part that A is maximal ideal. Euclidean ring R. Then we have to prove A naught is prime element of this Euclidean ring. Let, if possible, A naught is not a prime number, is not a prime element or number. A naught is not a prime element. This means A naught can be written as like this. Let P be an ideal of Euclidean ring R. But here we already let that A is maximal ideal of R such that it can be written like this. A is maximal ideal of R. So when this condition is written, either A will be equals to P or A will be equals to R. Taking first condition, that means P belongs to ideal this. It means P is equals to, let this ideal be generated by element P. Then 1 belongs to this ideal which is generated by P. So 1 is equals to any element. P is equals to ring R. So 1 belongs to ideal P generated by this element P. So 1 can be written as multiple of P. It can be said that P is invertible. P is invertible. That means P is unit element. Because from this point if any element A of Euclidean ring R is invertible, then it is an unit element. P is invertible, so P is a unit element. Here, let A is not a prime number. If possible, A is not a prime element. It means it can be written in products of two numbers where P and Q both are not equal to unit element. From here, so P is a unit element from this fact. But here we let that P and Q both are not unit elements. It means this is a contradiction because P is not a unit element by our condition. Now let us take the second condition. Ideal A is equals to ideal P. Then ideal A is equals to ideal P, or we can write ideal P is equals to ideal A naught. It means that an element of this ideal can be written in product of A naught. Make it third equation. This is the second equation and this is the first equation. Then from first and third, here P is equals to A naught Y. Here A naught is equals to PQ. So A naught is equals to putting value of P A naught Y into Q. A naught minus A naught YQ is equals to 0. 1 minus YQ is equals to 0. 1 is equals to YQ. It means Q is invertible, which implies Q is unit element. From this point, if any element A of Euclidean ring R is invertible, then it is an unit element. But here P and Q both are not unit elements, so this is also a contradiction. Both the conditions are resulting into contradiction. That means our assumption is wrong. A naught is not a prime number. This is wrong. So A naught is a prime element. Hence the theorem is proven by both sides. Thank you.